Firstly, thank you to Nathan and Rob for giving us this opportunity. The company I represent, I'll explain in more detail as I go through the presentation. But myself, obviously Al Goodwin, my background is not geological, so apologies there. If there are any geological questions that I can't answer, I've got experts on speed dial, but I'm getting quite good at this. I've actually only been in the industry for just over a year as well, so my background is actually in military engineering, so it's a far cry for what I'm used to. So I won't make any apologies. I worked with explosives, so I gained a sense of humour as an engineer. And I know there's loads of engineers in the room, so you know what I'm talking about there. The company I represent is a Canadian-based company. We're based in Prince Edward Island, and I'll take all the jokes about that later on, but I do like potatoes. And the company is a subsidiary of a Scottish-based technology company. Now what we've got is a beam that we push, a beam of energy we push into the ground, which can tell us what is in the ground. So it can identify any material and hopefully quantify. But the limitations and the advantages of that obviously will become more clear as I go through the presentation itself. When we set the Canadian company up February last year, I was very surprised that as a company that's been around for about 15 years, we weren't very well known in the mining sector. So for Rob and Nathan to give us this opportunity to talk to some of our peers in that sector is absolutely amazing. So again, I need to thank them for that. The oil sector tends to know us a little bit better and we use more in that, but we have done a number of mining jobs, mining projects, which hopefully I can give you some examples of as we go through. So as I said, the technology itself is a beam of energy that we push into the ground, and hopefully in the next 25 minutes I can help you understand why it does it, hopefully sow the seed of the potential capability that this technology has, and obviously hopefully find some work for it. So where it came from. The gentleman you can see in the picture is Colin Stove. His background is actually remote sensing, so he's an image specialist. In the 70s and 80s, he worked extensively with the British Ministry of Defence, the European Space Agency and NASA. And on one of the particular experiments they were doing, they were looking at ground penetration from satellite imagery. Now I need to stress at this point, because the presentation I gave earlier this morning, they thought we look at satellite imagery. We don't. This is just where it came from. So when they were looking at specifically some images from the space shuttle and from satellites, Colin found that he pressed a button that did something that created depth penetration. And he was able to see this because he went across an estuary in Scotland and he could see the pipeline running under the estuary within those images. Now bear in mind this was late 70s that we're getting this technology. He then spent from then until 15 years ago trying to figure out what button he pressed which was wrong, which gave him this capability. So from those early days, which was to do with polarisation of the beam, we now can, well, we've been proven to 5 kilometres of depth penetration, so it's a massive leap forward from where we were in those early days. Technology's failed me from a technology company. Okay, so what we do is, if you could imagine, if you will, a bag that we fill up with various different frequencies, we then pour that bag of frequencies into a conditioning antenna. And the antennas rely on an optical method of conditioning that beam. So very similar to a laser lining up the photons so that it can emit a coherent pulse, we do exactly the same with the photons within the energy frequencies that we put into our antenna. So if you like, it's a maser because we're using microwave type waves as they come through. What this gives us is this coherent pulse of energy that we can then emit into the ground. That pulse does a number of things as it goes through the materials it's interacting with. One of them is it creates a resonance. So at the atomic level, and this is where the term ADR comes from, atomic dielectric resonance, at the atomic level we get this vibration of the materials. That vibration does two things for us. The first one is it allows the beam to pass through without dissipation of energy, What it also does is gives us a signature of those particular materials it's passing through. So each material has a signature which is unique to that material within that resonance. What we also see is the slowing down of the beam depending on the material it's passing through. So as it passes through, it slows down at a different rate based on what that material is made of. That's called dielectric permittivity, and we can measure that as well. We also know the energy and frequency of the waveform that we're pushing out, so we can see the differences in the reflections that have been affected by the materials that they're passing through. The final measurement that we look at, this is light energy that we're emitting. So it's a radar technology, but it's being emitted at the speed of light. Therefore, we can use that light energy and its interaction to be as a spectrometer. So we can see the spectral lines of the materials we're passing through as well. The dielectric resonance itself is not new. So this has been known about for a long time, this resonance at the atomic level. And it was used on this experiment, and you can see from the bottom picture that the ESA were picking up structure at 3.7 kilometres in the surface of Mars. So they were using this exact idea. What they couldn't do was say what that was. So all they know is that there's something down there, but they can't say what it is. Obviously, with the additional data sets that we use, we would be able to say what it was. The physics behind it are not new either, so they go way, way back. But the best theories, if you like, that say why it does what it does, lend themselves to Feynman and the QED. So, okay. What we do with the pulse is we push it out as a wavefront. So we don't send just one out, we send out a number of them. And the more we send out, the more depth penetration we get. So it's almost like the first wave makes way for the next one to follow through and push a little bit further and so on. If we push too many out, it becomes saturated with the data we're getting back. So we have a fine balance of how many we can actually send out to get the information we want back. What we find though is that at every boundary, so when the material changes for whatever reason, we get these reflections back, and I'll show that in more detail as I go through the present. What we also find is between the boundaries we get a resonance of the beam as well, so that bounces back and forth, if you like, between the layers, and that's picking up these data sets that we can then interrogate later on. And what we get in the field, and the reason for this slide is just to show you that we get this stacked data back. The reason for this slide is just to highlight the fact that in the field we can't tell you what we're seeing. So this is just data. That's right. So this data that we collect in the field fairly quickly then needs to be sent back to Edinburgh, and the team in Edinburgh pull it apart. They look at 9 different data sets within these grey lines, and they can then do a forensic analysis of what they're seeing so that they can start to answer the questions that are required. The dielectric constant, or this dielectric permittivity that I talked about earlier, if you look at the screen and the table I've got up here, air doesn't slow the beam down at all, so we give that a scale of 1. Water slows it down the most. In this occasion it's seawater, so we give that 81. What you can see in the middle is pretty much everything else. So this slide straight away highlights what I was saying at the beginning, where one measurement won't give you the answer because you can see that the numbers overlap. Also, if we add any amount of that to any of these, those numbers creep up. So the wetter they are, the higher those numbers go up. Where this can become a powerful measurement though is if we can get access to a drill hole that has a core. So for example, 1,000 metres, we've got a chunk of core from that 1,000 metres that's limestone. We can put that in a chamber using the same technology, and we can get a number of that dry core. What we can then do is look at the field data at the same depth, and if, for example, we got a 5 in the chamber, but in the field data it's 65, then we know it's limestone that's extremely wet. So if we were looking for an aquifer, absolutely ideal. So that's just one measurement that this is capable of. And to highlight that further, this is client's log, and just one measurement is the dielectric constant you can see on there. And with the exception of the first one, there are some anomalies. You can see that as it goes into the aquifers, you can see that we get this increase in dielectrics, and then it drops off again, and then it comes back in again. And I've got some more examples of that later on. This one was a job we did for Tech in Northern Ireland, and again, all we're looking at is this one measurement of the dielectric constant. But this was proved by drilling, and all of the peaks that you can see on the dielectrics, so we're getting these high dielectrics, corresponded exactly to fractured ground within this hard igneous rock. So there's two things that you get from this slide. One is we're not seeing the fractures, we're seeing the water in those fractures. The other thing is it can go through hard igneous rock, as acoustic systems like seismic struggle with. This actually likes the high resistivity of thing. It's less good with the lower resistivity. So we're completely adverse to seismic. Okay, this one is just an example of how they can look at, there's loads of wiggly lines on there, I know that. But what the guys do is now we've got 3 measurements that they'll look at, and as I said, they look at 9 different measurements. And what they'll do is they'll pick out similarities in those wiggly lines which correspond to the geographical layers as they go down. Once they understand what those differences are, then they can find that over and over again. So it's a case of training the system to do it. So how we do that, as I sort of hinted at earlier, we've got a chamber, well we've actually got 2 now, and they're based in Edinburgh, but they can be taken out into the field. However, they're full of mirrors, so they're quite fragile, and they don't let people like me use them very often. But what the chamber is it's a 20 nanosecond chunk of the technology. So if we put material into the chamber, we can take a 20 nanosecond fingerprint, if you like, of that material. We can then divide up the field data into chunks of 20 nanoseconds, and we can look for those fingerprints within that. So this is another measurement that we can add to all the other ones that I've talked about to try and build up the picture that we're doing. And there's some examples of these 20 nanosecond chunks. All of our measurements are done in the time domain. So that's the reason why the nanoseconds have crept in on this. What we can also do is look at the spectral energy, or the spectral lines and the frequencies of the materials. So because of light energy, you can see from this chart that we can pull apart chemically quite close materials, and we can actually see the differences in those. One of the questions I've been asked quite a lot recently was, can we therefore identify a sulfide layer and then do an assay on it? In the chamber, we could, for this reason. Take that into the field data, it becomes far more complex because the differences are so subtle that there's a high degree of chance that we would get it wrong. So we don't offer an assay service in the field. Finding the sulfide layer, no problem. This one's probably more relevant to the audience we've got here today, because you can see materials that you're all familiar with, and you can see again that we can pull these apart. The other thing we can do with the spectrometry side of the technology is we can use public databases that are out there on the internet. So all of the spectral lines, spectral frequencies for elements are there available, so we can look for those similarities within those data sets as well. Okay, technology will fail me on this one, so I need to go here. Okay, what we've got here is in the top of the picture, you can see that's a representation of this waveform, this pulse that we send out. And this is a theoretical model. So what we've got at the top is surface going down into the ground. And what the simulation will do is it will show you the pulse going down through the ground as it goes. So it will highlight this bouncing back and forth that I spoke about. But what we've also done in the theoretical model is we've introduced a really high dielectric layer. So you could imagine it as a wet layer or a really conductive lens. So you'll see the reflection that we get back from that is extremely strong, but you'll also see the beam pass through that as well, as long as I can get it to work. So as I said, you can see a very strong reflection, but then we're getting bouncing between that, and then you can also see that we get this bouncing back and forth with the others as well. All of this resonating between the boundaries is collecting more data that we can analyse. It'll be easier doing this. Okay. One of the theories about an EnType pulse is this going through materials that are highly conductive or things like seawater is it shouldn't be able to do it. So we've got a Toronto-based geophysicist, a gentleman called Peter Walker, which some of you in the room might know. He's doing an independent study of what we do to try and write a paper that says either it does work or it doesn't. It looks like it's going to be it does, okay, but we haven't got the paper yet, so I can't say that. Spring in Prince Edward Island, and what we did, this was last year, we cut a number of very large holes in the sea ice. We used the sea ice because it's a lovely stable platform, basically, so it's a perfect laboratory, albeit it's a little bit chilly. And all we did is we put the antennas into waterproof casings, and quite simply that's the receiver, and that in the distance is the transmitter. This was in air, transmit there, collect there, it must have passed through that material. So in air, obviously not a problem. What we then did is flip those completely upside down, so the antennas are now 2.5 metres below the surface of the ice, and did the same again. And we stepped out progressively out to 500 metres. So transmitting, receiving, eureka moment at 500 metres when we got the pulse into the receiver. So we were like, yeah, we've gone through 500 metres of seawater. However, there's a high chance that because of the configuration of the waterproof casings that we did, we gave it an easier path to take. So it probably came up out of the water, through the air, back down into the water and got collected that way. So this year, I had to go out there again, and this time we put a massive amount of shielding around these so that it couldn't have that easy path up through the air to try and disprove that potential theory. And I haven't got the results on that, but it's looking good. The point from it all, though, is it did go through 5 metres of seawater, even if it took the easy path, because it's had to come up through 2.5 and go back down through 2.5. So it's still doing stuff that it shouldn't. What we also did on these experiments is, on the wharf that you saw in that picture nearby, we did a more traditional survey of looking down into the ground. And what you've got in this picture is we're going through 18 inches of reinforced concrete, through the air, through the sea ice, into the seawater, and this again is only one measurement, but this is a dielectrics again. So you can see we've got this increase of the dielectrics as it goes into the seawater, dropping off as it goes down through the actual seabed. Then it peaks again as it comes through what is actually a freshwater aquifer, drops off, and then it's coming up again as it goes through a seawater. Basically it's a saltwater aquifer. And then we didn't track any further, so there could be more, but we haven't looked. So this highlights straight away that the beam is passing through the seawater and the freshwater. And we know these are there because there's a borehole nearby, and they actually use it for geothermal heating of a building. They're using the warmer seawater. So we know these depths are accurate. Must be my computer. This is how we carry out normally a project with a client. So stage one is to understand exactly what the question is. So we try to work with the client, and that can be quite a long, protracted affair to figure out exactly what we need to answer. Point two is where we may use the chamber if there's access to a core that we can put into the chamber. If not, we can use other data sets to try and truth what we're seeing. So we can use downhole logs, we can use mud logs, we can use seismic, anything that's available. We've also got a database that is getting bigger every time we do a project. So if there was no data available to truth what we're seeing, then we can look into that database as well. Stage three is where I normally come in, looking after the operational side, and that's us going out into the field. So one virtual borehole, as I'll call it, so it's akin to a drill hole, will take me about 2 hours to collect the data in the field. That equates to about 4 or 5 days post-processing from the guys in Edinburgh. So the longest part of the process is them guys. And then they do 4, 5 and 6, which is normally a lot of bouncing back and forth between data sets and understanding exactly what these differences we're seeing in the data mean, so that they can then produce a report which hopefully they get right. The equipment itself, the reason for this slide is to show you it, but also to highlight how portable it is. So we can scan anywhere you can walk. It's literally that portable. So what we've got here is a pulse generator. So that's taking these frequencies that we decide, and I'll come on to that in a moment, depending on the depth we want to go down to. They go into the transmitting antenna, and using optics, that conditions those frequencies into this coherent pulse. Obviously that's then emitted out of the end of the antenna. The receiving antenna is identical in construction, and this collects the reflected beam as it comes back up. It deconditions that, if that's the right term. It probably isn't, but hopefully that highlights it. And then it feeds it into the receiver control unit. The receiver control unit does two things. One is it obviously digitizes all of this data that we get back, and we collect that on a small palm top computer. What it also does is allows us to set up the pulse so that we can change the frequencies, the gain, the amplitude, so that we can focus it on the depths that we're interested in. What we also do, and I don't know if you can see this other cable that's coming out, we trigger each pulse. So every pulse we send out, and we normally send 500 out on a normal survey, each one is triggered so that we can get an idea of which one is creating those reflections as it comes back up. What we can also do then, as I said, we normally do about 500, but we'll do a number of those sets of 500, so we can stack those up. The advantage of doing that is it reduces the signal to noise ratio, so it gives us purer data if we stack up more. If we tried to do it as a one-off, the computer would probably crash, but also what it does is it gives too much information, so it can become counterintuitive, and the guys would really struggle to pull out those differences from those data sets. So the advantages of using us: low energy. It is less than 5 milliwatts that we push out, so it's incredibly low energy that we're using. Part of the secret why it can do what it does. It is non-destructive. I told you already I've got a military background. I didn't want to grow another head after using this for 2 years, so we had it tested by the Ministry of Defence. So we know it's completely non-destructive. We can go anywhere you can carry it, so literally all we leave behind damage-wise is footprints. Some of them can be quite deep if you're in muskeg, but they're still only footprints. And as long as we avoid the orchids and the rare flowers, we're actually non-destructive. So environmentally, this is amazing because it does no damage. A couple of projects we are working on are areas where other technologies can't be used. So this doesn't mess with the navigation systems of the beluga whale, for example. So where noise is an issue in those sort of projects, we're working on those. Other areas are where they don't want to be putting drilling rigs for no reason in areas of natural beauty, or where there's things like First Nation people that are getting upset about it. So again, this has got a massive advantage to it because it's lightweight. What we try to do is, as I said before, we don't replace drilling because you're always going to need to drill, not least for your permitting issues. But if you do 10 drill holes to get one successful one, why not do 9 virtually at a fraction of the cost, so that your one successful drill hole is the only one you need to drill. So that's the service that we try to offer. And what I've got is a few case studies, which I'll just skip through. But what I'm trying to do is just give you an idea of where we've used this in the mining space so that you can see that the potential is there. I focus quite a lot on water. The only reason for that is because water gives such a massive difference, so it gives me such good examples. However, please don't lose sight of the fact that it can identify any material. So therefore, where we're seeing such massive changes with water, you can also see these subtle changes with other materials. The Teck underground example was in their Ponderay mine in Washington State. And what they did, they invested in the parent company about 4 years ago now. And part of their test to see if they wanted to sign that check was put the equipment underground, and on this occasion shine it upwards. So they basically wanted us to look upwards through this tunnel. They wouldn't give any training information, so there was no way of truthing the data they would see, and they just wanted to see what we could see. On one of the 4 locations, the beam as it went up, so you can see at the bottom is the tunnel. We've got a very low dielectric. Again, this is just a dielectric log, but this was truthed by using other data sets as well. Coming up through, we can't confirm these are fracture zones. We just saw high dielectrics, but nobody knows if they are or not, and they weren't willing to drill it. So there's something there, but we can't tell you what it was. But as this particular one came up, we got a massive high in the dielectric before it went to the low dielectric of the area above. So the first thought was the data set was corrupt. They published it anyway, and it was actually tech had put us under a river in that one location, and they'd done that on purpose to see if you could see this data set. So that picture there was worth quite a lot of money to the parent company because tech signed the check on the basis of that. We've also done, and this will be of particular interest to a lot of you, we've done a lot of work with sulfides. That was Sudbury about 4 years ago, I believe. And they learnt a lot about looking for sulfides and porphyry type structures within the geological ground. So that was a good training ground, if you like. And there's some examples of different charts that they're able to produce. And again, here you're seeing, this is just an energy log, but you're seeing that we're getting energy peaks on this occasion, which is a different data set, but we're seeing another difference that can be correlated to geological structures. This one more important for us because this was done over the last 2 years, and it's a company called City Gold, which I'm delighted to say I can tell everybody about because they went public. And this was in Australia, and the particular sites they were interested in are under a town. So we're into this where I was talking about not being allowed or not wanting to use other technologies. This is why they wanted to see if this would work. And we actually presented this at the ASEG in February, and it's quite compelling. And I can make these presentations available clearly. I don't want to run out of time today. But we were able to intersect the sulfide zone. This one was easy for the technology because it was pretty much one type of rock and then a quartz vein. So the differences were massive, as you can see, on the low energy response as it picked it up. But they got accuracy of about 1 centimetre when they drilled these. So City Gold changed their geological model based on our results. First time that's happened for us, and of course that's amazing. As I said, they also went public, so I can make that available if anyone's interested. Another job that's been ongoing has been looking at coal bed methane. BG Group, this is an ongoing project with us, and it's been going for about 5 years actually, but they were interested in the early days to see if we could see the difference between the wet shale and the wet coal, and other technologies can't. So I'm conscious of the time, so I'll just skip through, but more wiggly lines that correspond to a stratigraphy chart that we can produce. And that's the reason for this slide, is just to highlight this is one output that we can push out that just gives you your stratigraphy as we go down. BG Group did some blind tests on us, and these were their conclusions. And the shale does look like coal, even in our energy responses and frequency responses as well. But we were starting to see these subtle differences. Add in the spectrometry that I talked about earlier, and we're actually starting to pull it apart, and we can actually see those very subtle differences. That's a very busy slide that says, yeah, you're not doing too badly. So I'll skip past that one. What I do want to highlight though, the actual survey area was quite big. So what we did on one area, and it was about 100 square metres, was we did a whole field of virtual boreholes. And the reason for this is they wanted a three-dimensional geographical representation of what we are. So where we're normally producing just a one-dimensional set of data, by doing this, we were able to link them all together and give an indication of the structure within that ground as well. If you tried to use it on a very wide scale, it would become too expensive. It's as simple as that, with all the processing that would be required. But it does show that it is possible. And the final example I've got is of geotechnical work, again with tech, for obvious reasons. What they've got is a lot of coal mines, as I'm sure you're aware, over in British Columbia. This particular one, Coal Mountain, they'd got man-made structures and geological faults that they knew about. So they wanted to put us alongside it and see if we could identify them. So this time we did it horizontally, and we were looking for obviously the air in the tunnel and something in the fault. We didn't know what. One measurement and you can see the air. So where I said earlier, one measurement won't give you the answer, I lied, because there it does. Because it's so different, it was so obvious. So the air tunnel, very, very easy to find. The fault, less so, because there's a high chance there's no gap at all. So it was just a shear in the rock itself. But even from these individual charts, you can see that they were able to pull out various different data sets that pretty much highlighted where the fault was. We're not sure what we're seeing in that fault. So it could be air, it could be water, it could be some form of mineralisation that's formed in between. We don't know, but we can see the fault is the point from that slide. And from that, the guys were able to accurately say exactly where that was. So for tech's interest, I mean, they routinely have trucks falling into holes in their coal mines that were either old workings or geological faults. Not least the fact that that's probably dangerous, and these trucks are really big, as I'm sure you're all aware. It's also $1 million a day lost production, so it's expensive for this to happen. So they're building a whole geotechnical program with us to be able to try and look and see if we can get these so that their trucks don't fall into them. I was chatting with Nathan earlier, and we were talking about water again, because it does give us such massive differences. And one of the projects we're currently doing is with the Camborne School of Mines and a company called Imerys, which are a French company that mine China clay in Cornwall. And their interest is actually a river running behind the pit to see if we can see where this water's coming through, because it's giving them slope stability issues. So it's another geotechnical issue. But if we can map that for them, then they can obviously put drainage channels in. What it means is that they can extend the life of the pit, because they can take bigger risk on the angles of their slopes. So they'll extend the life of the pit by about another 5 years, which is obviously economically amazing if we can help them. We're also looking at the degree of kaolinisation within that granite. So from the really soft stuff right through to the stage 5, which is the really hard stuff. Can we see the differences? And it looks like we can. So even though the material is the same, albeit it's been changed, it's still chemically the same material. We're seeing that degree of softness within the data sets. And that's it. So I'll now gladly take any questions.
I got a whole page. But the last one that might be more general interest. Have you used this technique for exploring for volcanogenic massive sulfide or VMS deposits?
Yes, I mean the City Gold itself was one example of that. We've done others in Nova Scotia. They've done some work, very, very limited at the moment, but we've looked at areas in Nevada, hoping to get a few more north of here. So yes, we have, is a simple answer. And obviously I can make those data sets from City Gold I can send to you. I've got your card anyway, Jim. So yeah. And the same for anyone else if you want. There's some cards laying around and some brochures, but I've got more here. So if anyone wants further information, just let me know and I can pass that on.
What's the reason why you have to send all the data back to Scotland? Is it a computing power issue, or is it an expertise in the room you need to understand it?
It's forensic. It's not there is no software solution to look at 9 different data sets and decide what those differences are. We're working on that, but we're not there yet. So once we can, one of the things they have to do is track what we call a wide angle reflection, which is basically it's an MNO from seismic type world, where we do a step out so that we can triangulate, so that we can get accurate depth measurements. They have to track that by eye. And that takes a long time.
So is it an iterative process? Data goes back and forth during the field trials?
Yeah, each data set's about 4 megabytes, so we just email them. Yep.
And every night they get data and they tell you, okay, tomorrow.
That's exactly what it is. Yep. Yeah. So if we're the right side of the time zone, it's brilliant because they just do their day job. Yeah. If we're the wrong side of the time zone, they have to stay up late. But yeah.
Can you comment on the angle? I presume it doesn't have to be vertically.
It doesn't. As you probably picked up on the geotechnical one for tech, we did horizontally. So It's not as pinpoint as a laser, I'll make that point now, but if you imagine a laser, pretty much where you point that is where our beam of energy is going to go. It's actually a bit bigger than that, and it's focused as it gets deeper, and this is because the waveform gets compressed, but yeah, wherever you point it is where you can look at.
What kind of depth can this penetrate to?
It's proven to 5 kilometres, so that was on a gas play in Morocco, but it's been proven to those depths. Yeah.
How the presence of
Sorry.
how the presence of geotechnical features like faults and things like that might influence the interpretation of the results?
As long as we know they're there, then we can see what those differences mean. So if you've got a geological fault that, say, contains water, then we would get this high dielectric as one measurement. We'd also get a high energy peak from that water. But then, as long as we know it's there, you can discount that and say, okay, that's fine. The beam will continue to pass through that. So it makes no difference at all, as long as we know about it. So we can discount those changes. Or if that's what you're looking for, then you found it.
I have not seen your analytics. I mean, what I saw, it's just...
Yeah, they're just broad examples here.
I don't see the 3D model and how you connect what your technology provides with drills or drilling costs like that.
Yeah, if you imagine that we are producing a one-dimensional set of data, which is like a drill hole. So if you take loads of drill holes in a grid pattern, and then you take all of that data, then you can build up a model. Clearly you don't know what's between those drill holes, but depending on how close you put them together, you can get quite accurate. So if you've got really complex geology and you know, dipping quartz veins and stuff like that, then clearly you want them really close together so you can start to track them. If you're looking at the example I had there, which was coal bed methane, it's fairly benign. So to map that, you don't need them as close together. But that's how we would do it if we did. We don't tend to do that because it's expensive. So if you can get that same information from seismic, why would you use us? You know, that's the point. So ours is really, it's a one-dimensional set of data that we provide that can be used in lots of different ways.